All right, everyone. Over the last couple of days, we've looked at the concept of gravitational fields, which will differentiate fields from forces. Okay, similar, not the same thing. Remember, a field is a line of influence that surrounds something with mass. A gravitational field, at least, is a line of influence that surrounds something with mass. And it's there no matter what. As long as you have that object with mass, it's going to cause the gravitational field lines surrounding it. It's going to cause other objects to be attracted to that object with mass. It's there no matter what, the field. Now, force, on the other hand, is also there. There's also a force of gravity if there's something there to experience the field. So, the field are these blue lines that are there as long as you have something to cause it. The force is that influence that's felt by this little red object as a result of the field. Now, the force of gravity that acts on this big blue mass or this little red mass is equal to gm1 m2 over r squared. The force on one of them is exactly the same value but in opposite direction to the force on the other one. The field that's produced by the mass is equal to gm over r squared, m being the mass of the producer. The field experienced by this little red mass, if the little red mass is there, is g is equal to f over m. These two equations go together, but recognize that you're only going to use one of them. Okay, you want to find the field. You can find the field using information about what caused it or information about what experienced it if you have something there to experience it. Use one or the other. Okay, whichever one you have more data for. G is G. This equation applies to a different situation. Okay, here we're not trying to find the field that's caused by this big blue object or this little red object, but rather we're trying to find the force, or what's another term for force of gravity? That starts with a W. Wait. Who can do this? Wait. What is it? Weight. The force of gravity that's felt by either one of them. Does that make sense? All right. Didn't spend a lot of time reviewing that this morning because we've done that the last couple of days here. We had a couple questions, 3 questions actually, on page 220 to do for homework last night. Any issues with any of those 3 questions on page 220 that we need to go over here now? Lewis? Or 3? 2B? Let's just take a look at all of number 2 there and number 1. Okay, let's take a look at all 3 of them. Okay, let's take a look at number 1 here. What would be the weight of a 22 kilogram dog at the equator on Saturn's surface? I'm not sure exactly where these questions come from sometimes. Like, who, as they're writing this textbook, says, let's put a dog on Saturn and find out how much he weighs on Saturn. But it is what it is. Okay? It might not be so much a practical question because usually we don't have dogs on Saturn, but it's a question that we can still do. What are we actually looking for here? What's another term for weight? We just talked about that in reverse, right? Weight is the same thing as force of gravity. Yeah, the force of gravity. Not field, but the force of gravity. So if we want to find the force of gravity, really we got a couple of options, right? It's m times g, or it's gm1 m2 over r squared. Which one do you want to use here? They're both valid. Which one do you want to use? First one or the second one? I'll tell you which one I want to use. I want to use the first one because it's a lot less math. But I'll tell you which one I'm going to use. I'm going to use the second one. How come I'm going to do what I don't want to do? How come I'm going to use the second equation when I really want to use the first one? They're both valid. So why not just use the first one? Yep. I don't know what little g is. Now, could I find it? I could. Yeah, I could. I could turn around and say, look, the gravitational field produced by Saturn is equal to big G m, the mass of Saturn, over r squared. Get the value of little g, plug it into there, find the force of gravity, done. But if I'm going to have to go to this step, I might as well just find the force of gravity this way, right? F is equal to gm1 m2 over r squared. They both work. Two different ways of arriving at the same thing. All right, big G is 6.67 times 10 to the minus 11. Mass 1, doesn't matter whether mass 1 is the dog or whether it's Saturn. Call it the dog since that number is up there. What's the mass of Saturn from that table? 1.90 times 10 to the 27. So about 1,000 times heavier than the Earth, right? The Earth is 10 to the 24 kilograms, it's 10 to the 27. What's the radius of Saturn? Remember that R doesn't stand for radius. R stands for distance from the center of the object to wherever. Okay, but if you're looking at the surface of Saturn, then the distance from the center of Saturn to the surface is the radius as well. So that's what we're looking for there. Don't forget to square that. If you do the math there, not forgetting to square that distance, and we should end up getting 230 newtons. Interestingly, the dog on Earth would weigh almost as much, about 220 newtons. Can anybody explain to me, despite the fact that Saturn is 1,000 times heavier than the Earth, why gravity is only about 11 meters per second squared, as opposed to about 10 like it is on Earth? Why is it not that much bigger when it's so much heavier? Zach? The radius is bigger as well. Good. So really it comes down to both, right? And radius is more of a factor than mass is, right? We talked about that because it's r squared. Good. Okay with that one? Okay, 2A. Do you think, this is just a think question, right? Kind of a guess, a hypothesis. Do you think your skeleton could support your weight on Jupiter? Do you think it could or couldn't? Who says yes? Who says no? Why don't you think? Okay, most people are saying no here. Why don't you think that your skeleton could support your weight on Jupiter? Any reason, or is it just kind of a guess? Yeah. So the field strength on Jupiter is going to be pretty strong. Okay, so your bones are used to a gravitational field strength of about 10, right? 9.8 meters per second squared. And you're saying that the field strength of Jupiter is going to be a lot bigger? Okay, but you think it's going to be bigger? Okay, which means that your bones would have adapted over millions of years to hold the weight according to gravity on Earth, but wouldn't adapt quick enough to support your weight on another planet where the gravity was a lot stronger. Okay, that sounds good. Yeah. Oh, is that right? Okay. So guys, just so you know, the answer is 230, but we don't get 230 when we do the math here. Lewis just pointed out that he gave me the wrong numbers right here. He gave it to me for Jupiter as opposed to Saturn. So when you do these numbers, you don't get that number. But if you use the actual numbers for Saturn, you get that, right? So that's fine. That's fine. Mathematically, it doesn't quite work out because of that, but conceptually, it's the exact same thing, right? Okay, so back to question number 2 here. Stephanie gave me what seems like a pretty good answer for that, right? Like our bodies just aren't adapted to handle a gravitational field strength that's a lot bigger than 9.81. What do you say? Yeah, basically, yes. I mean, besides atmospheres and all kinds of factors that would be a problem in moving planets, right? Temperatures and adaptivity to temperatures and all that kind of stuff. Just pure strength-wise, yeah. If our body was adapted to something that was, say, Jupiter, which has a much stronger force of gravity, then yeah, you come to Earth and you'd feel so light. It'd be like us going to the moon, kind of thing. You see the astronauts on the moon, they're jumping around, right? And they jump 6 feet high, like nothing, right? Because they weigh so little. Their legs are so strong for the moon. Right? They're used to. I'm used to lifting 150 pounds of weight with my legs, but if all of a sudden I'm on the moon, then all I have to lift is 25 pounds, which my legs are way stronger than that, right? I can lift 25 pounds really easily. I could jump really high if all of a sudden I was 25 pounds. Right? Okay, so let's calculate the field strength Well, let's calculate question B. Compared to Earth, how much stronger would your bones need to be? To do that, we're going to calculate the field strength on Jupiter and on the Earth. You know what? We already know the field strength on Earth, right? 9.81 meters per second squared. We'll go with that number. Yeah, I'm not sure whether they're actually looking for you to calculate it here or whether they're just looking for you to use the accepted value. We'll just use the value you already have. Yeah, you could find it in the exact same way as you'd find the field strength caused by Jupiter. Gm over r squared. 6.67 times 10 to the minus 11 times the mass of Jupiter. And I know you got this one. 1.90 times 10 to the 27 divided by r squared. What's r? And we got to square that. What does that work out to be, by the way? Hold on. I'm gonna take a stab at this. I'm gonna say about 25. 25 meters per second squared. Oh. Okay, so 24.9199. So I was pretty close there, right? Meters per second squared, or you could say newtons per kilogram. Hey, anybody know how I got that so close? Anybody know how I got that so close? Am I able to multiply these numbers and divide that, square that in my head? Not a chance. Not a chance. How did I get so close to that when I said 25 meters per second squared? Yep. I didn't remember that, to be honest, if that's the case. I mean, it is obviously clearly, but I didn't remember that. No. $24.789. Let's just double check that. So it looks like it is 24.789. Newtons per kilogram or meters per second squared. Regardless, I was pretty close, right? How did I get it pretty close? Well, I cheated. I looked at the answer and saw it's 2.53. So what did I figure? I said, well, okay, if gravity on the Earth is about 10, and gravity on Jupiter is 2.53 times more what is on Earth, what I got to do? Multiply by 2.5, right? So 10 times 2.5 is 25. Well, they're actually looking for us to go the other way around. You want to compare, then divide. We're going to say the gravitational field on Jupiter is 24.789. We're going to divide it by the field strength of Earth. We get 2.53. So that means you could write it as a ratio, 2.53 to 1. Or you could just say that the field strength on Jupiter is 2.53 times what it is on Earth. Or you could say that your bones need to be 2.53 times stronger than they do on Earth. That would hurt a lot. Your bones wouldn't necessarily break, okay, but not immediately. They wouldn't break immediately. But it wouldn't take very long for your body to ache so badly if you experience this gravity for more than several seconds, okay? Because it's like you go and lift weights. What happens? Eventually, your muscles get tired, right? Here you'd be lifting 2.5 times your weight all the time, constantly. So you get so tired so quickly that probably your muscles would weaken. You'd end up tearing muscles. Your bones would weaken. You'd end up breaking bones eventually. That would happen. Probably not too long either. Yep. Well, yeah, it's the heaviest, but it's also the biggest radius. So I'm not sure how that balances out, to be honest. I would suspect the answer to that question would be yes, but I'd have to actually crunch the numbers to make sure. Let's take a look at number 3. The magnitude of the field strength at the equator on Uranus's surface. Who's got the value of this planet? The value of the mass of this planet? Uranus. .68 times 10 to the 25 kilograms, right? And the radius is 2.56 times 10 to the 7 meters. We want to find the field strength there, right? Is the planet the producer or the experiencer of this field? It causes the gravitational field, right? So we're going to use the producer equation. It's big G m over r squared. And that constant, always the same, times the mass, 8.68 times 10 to the 25. Divided by the radius, 2.56 times 10 to the 7. Don't forget to square that. And I assume when we do the math there, we end up with 8.83. So we've got a, we're going to go newtons per kilogram. We could go meters per second squared as well, right? We've got a mass that's about 10 times heavier than the mass of the Earth. So this kind of comes back to what we asked about one of the other questions. Why is the field strength actually a little bit less than what it is on Earth, despite the fact that the mass of the planet is more? Anybody have an answer for that? Why is the field strength less, even though the mass is more? The radius is bigger. And what matters more? The radius matters more, right? Good, because it's squared, right? Okay. Compared to Earth, how would your weight change? Well, compare means divide, right? So we're going to divide the gravitational field strength on Uranus, 8.83, and we're going to divide it by the gravitational field strength on Earth. We won't recalculate the field strength on Earth. We'll assume that it's 9.81, although we could calculate it in the exact same way as we did here for Uranus. 8.83 divided by 9.81 gives me 0.903, okay? Which means you could say it's a ratio of 0.903 to 1, or it's 0.903 times the field strength caused by the Earth. Now, they're asking me to actually compare weight, not field strength. But weight is m times g. So if we come up with a ratio of field strength to field strength, that's going to be the same as the ratio of weight to weight. So we could turn around, we could calculate weight from this and from 9.81 based on what your mass is. Okay, but in the end, comparing the field strengths is exactly the same as comparing the weights, right? As long as we have the same object on that planet. Is that good? Yesterday, we defined a satellite as anything that revolves around something else. But of course, when we talk about satellites, we're going to be talking about satellites that are in space, right? Not a car going around a racetrack, but rather a planet going around the sun or a satellite going around the Earth. Those satellites are all kept in orbit by a centripetal force, but that centripetal force is caused by gravity. So in the end, the way we're going to analyze this, whether it's a natural satellite like the Earth revolving around the sun, or an artificial satellite like a communications satellite or the International Space Station orbiting around the Earth, the way we're going to analyze both of those questions is by setting Fc equal to Fg. The centripetal force, that force that keeps an object going around in a circle, is caused by gravity. So those two forces have to be equal to each other. Now, yesterday we plugged in some variables into these equations. mv squared over r is equal to, we could say m times g, but we don't know what g is. It changes depending upon how far up you are. So it's easier just to say g m1 m2 over r squared. One of the r's cancels, and one of the m's cancels. If we call this the mass of the experiencer, the mass of the satellite, and this is the mass of the satellite, then they cancel. Okay, that leaves me with v squared is equal to big G times m. That would be the mass of the producer over r. And what we're going to do now is rearrange to solve for whatever variable we're looking for. Usually it's v, okay, but oftentimes it's r, and occasionally it might even be m, the mass of the planet that you're orbiting around. All right? Here's a question. It says the Earth is this far away from the Earth. The moon is this far away from the Earth. We're in kilometers there. We don't really want that, right? We want meters. So I'm going to circle that to draw attention to that, to remind me. We want to find the speed of the moon. Now, we know that v squared, we just derived an equation. We derived it to be v squared is equal to g times m over r. Okay? I don't want to just remember that and write that down now. I want to derive it again. Every time I see this question where I'm looking for speed, I want to derive the equation. It doesn't appear on my data sheet. Okay? I've got a terrible memory. If I try to memorize that equation, I'll probably end up messing up on my unit test or on my final exam. So what I'm going to do is remember simply that FC equals FM. Sorry, FG. And therefore, mv squared over r is equal to gm1 m2 over r squared. And r's cancel, and m's cancel. And what I'm left with is v squared is equal to g times the mass of the producer, which in this case would be what? The moon or the Earth? The Earth. Divided by r, not r squared anymore because I got rid of one of those r's, right? Looking for speed, I'm going to say v is equal to the square root of g times m over r. So let's plug some numbers in here now. V is the square root of 6.67 times 10 to the minus 11 times r. Okay, the distance we're going to use here is 3.844 times 10 to the 8, because we want it in meters, right? If you get 10 to the 5 kilometers, then you have 10 to the 8 meters. Sorry, you're right. Yeah. No, we're using the mass. You're right. 5.97 times 10 to the 24. That number is going to go on the bottom, right, Stephanie? 5.97 times 10 to the 24 kilograms divided by 3.844 times 10 to the 8 meters. We want the distance from the center of the Earth to the moon. They give me that distance. What if they had to give me the distance from the surface of the Earth to the moon? What would I have done then? Not subtract. I would have had to add them, right? If I was given this distance, I would have had to add that distance to the radius of the Earth in order to get that distance right there, the distance from the center of the Earth to the moon. And the good news is, I didn't have to worry about that in this question because I was told the distance from the center to the center. All right, let's do the math there. I'm going to open up the calculator again, and we're going to do this as a group just to make sure here. We're going to say, let's just do what's inside the square root sign first here. We got 6.67 times 10 to the minus 11 times it by 5.97 times 10 to the 24. Divide it by 3.844 times 10 to the 8. Okay, and then we got to square root that. 1,017. 1.02 times 10 to the 3 meters per second. So, how fast is the moon moving? Pretty fast, 1,000 meters per second. Okay, about 3 times the speed of sound, Mach 3, as it hurtles around the Earth. The reason we don't hear a sonic boom is because there's no air. You can't make a sonic boom if you don't have any air to make the sonic boom in. It's going 3 times the speed of sound, but no disturbance to make a sound. Okay, got it? All right. Let's see what you can do with those 2 questions, please. Let's take a look at number 2 here, guys. Or maybe not, since Lewis just managed to figure it out. Number 1. Okay, we'll take a look at number 1 here. Neptune's average orbital radius is 4.5 times 10 to the 12 meters from the sun, so it's a long ways away. The mass of the sun is this. What's Neptune's orbital speed? It's a satellite, right? It's a natural satellite. We say FC is equal to FG. mv squared over r equals gm1 m2 over r squared. One of the r's cancels. One of the m's cancels. We're left with v is equal to the square root of g times m being the mass of the producer, not the planet, the producer, which in this case is the sun, over r. So it's going to be 6.67 times 10 to the minus 11 times the mass of the sun. Seth, it's the mass of the sun, right? Not the mass of the planet. Why is the mass of the sun? and the mass of the satellite, which is the planet in this case, canceled out, right? Canceled out mass here, mass here. That's the mass of the satellite, the mass of the planet in this case. So it's 1.99 times 10 to the 30 divided by r, which is 4.50 times 10 to the 12 meters. Can you do the math there? Do we need to go through the math there, or are you okay with that? Good with it? Okay. So what was the issue with that? Did you have all that? All right. So let's plug it into the calculator then, just to make sure. We're going to say 6.67. Just follow along on these keystrokes here, okay? 6.67 times 10 to the minus 11. We're going to times that by 1.99 times 10 to the 30. Not negative 30. 30. We divide that by 4.5 times 10 to the 12. And we're going to square root that. 5431. Okay. Which we round to 3 digits, right? So 5.43 times 10 to the 3 meters per second. Good. All right. Okay. Yeah, we will take a look at it for sure. Okay, so we do need to go over number 2 after all. So we've got this moon orbiting a planet at a speed of 6.68 times 10 to the 3 meters per second. We got the speed. We want to find the radius given the mass here. So we're going to say FC. Once again, this moon is a satellite. The planet is the producer here. FC is equal to FM. mv squared over r equals gm1 m2 over r squared. Seems a little silly that I keep repeating the exact same thing, right? Okay, but the more you repeat it, the more likely you are to be able to do it yourself here. Let's cancel one of the r's here. Cancel one of the m's. I'm left with v squared is equal to g times the mass of the producer over r. We're looking for r. So now what we're going to do is take that up by multiplying. Take the v squared down by dividing. It becomes r is equal to gm, mass of the producer, over v squared. So it's 6.67 times 10 to the minus 11 times the mass of the producer, which is the planet, right? Because it's the satellite. The moon is orbiting around the planet here. Divided by v, which is 6.68 times 10 to the 3. Square it. Don't forget to square that. So let's do this one definitely on our calculators here. We're going to want to use some brackets on this one too. Let's go 6.67 times 10 to the negative 11 times 8.68 times 10 to the 25. We're going to divide that. I pressed equals there to get a number on the top. Let's divide that by bracket 6.68 times 10 to the 3. End that bracket, and now let's square everything inside the brackets. And when I do that, I should end up getting 1.31. Yeah, I get 1.32. I'm sorry. Oh, is that right? Okay, so it is 1.30 because I made that number wrong. It's 6.68 as opposed to 6.63. So that's going to change my answer ever so slightly, right? To 1.30 times 10 to the 8 meters. Bart, is that okay? It's a big distance, eh? 10 to the 8 meters. 130 million meters. Yeah. Yep. Yeah, it's Thursday, right next Thursday. Yeah. All right. Let's take a look at another one. Same kind of idea, but a little bit harder, and you'll see how it's a little bit harder in just a second. All right, another example, 5.12 on page 279 here. Similar, but a little bit more to it. It says Landsat is an Earth imaging satellite that takes pictures of the Earth's ozone layer and geological features. It orbits Earth at a height of 912 kilometers. That's above the surface of the Earth, right? What are its orbital speed and its period. All right, well, let's consider this as we have the other satellite questions to this point and say the centripetal force that's experienced by this satellite is equal to the gravitational force that causes that centripetal force. mv squared over r equals gm1 m2 over r squared. Exactly the same, isn't it? Exactly the same. V is equal to the square root of g times m. That would be the mass of the producer over r. What's the mass of the producer here? The mass of the satellite or the mass of the Earth? It's the Earth, yeah. So it doesn't matter what the mass of the satellite is because it cancels out. What matters is the mass of the Earth here. Let's figure this out. 6.67 times 10 to the minus 11 times the mass of the producer, which is 5.97 times 10 to the 24. It's on your data sheet. It's also on that table that you had from yesterday or the day before. R, what's R? 912,000, because we got to convert it to meters. Yep, okay. Good. It's 6.38 times 10 to the 6 meters plus 912,000 meters. We always want the distance from the center of the producer to the satellite. Okay, let's definitely do this one on our calculator to make sure that we can all do it. We're going to say 6.67. We're not even worrying about the square root sign yet. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. I'm going to press equals. I'm going to divide that by, now you definitely want to use some brackets here, 6.38 times 10 to the 6 plus 912,000. End the bracket. My answer? Is that my answer? Almost my answer, right? What do I got to do to finish this off? Square root it. Second function, square root. Answer, 7389.6.7. 7389.7. Which, of course, actually rounds to 3 digits. So 7.39 times 10 to the 3. That's pretty fast. 7,400 meters per second. 7,400 meters per second. 7.4 kilometers in 1 second. That would get you to downtown Calgary in about 5 seconds, right? We want the orbital speed. We got that. And its period. Oh, wait. Its period. How long does it take to orbit around the Earth? Any ideas for that? You guys can do this question. Okay, even though we haven't done one like this, you guys can do this. What's the orbital period? How long does it take to go around the Earth? Brian, what do you want to do? Good. Let's try v is equal to 2 pi r over t. Now, that is going to work for us. But even if it didn't work for us, it's a valid equation. So we're going to try something that we know is valid. See what happens. As I say, I know this one's going to turn out, but we're not going to panic about that if we're not sure. But we're just going to try it. 2 times pi times r, which is, once again, we got to use that 6.38 times 10 to the 6, plus 912,000 divided by the speed, which we just got, 7389.7. What are the units going to be for that answer, by the way? Period's going to be measured in seconds, right? If we're using standard units to this question, we got to get standard units for an answer here. 2 times pi times, let's use some brackets here for r, 6.38 times 10 to the 6 plus 912,000. End the bracket. There's the top number. Let's divide it by the bottom number, which was my last answer, the speed. 6,200 or 6.20. That's 10 to the 3 seconds. Now, you could figure out what that is in hours and days and minutes, but it's fine to leave it in seconds. In fact, it's probably better to leave it in seconds because that's our standard unit. Make sense? There's a good chance that you'll have a question where you got to do something with this. There's also a good chance that you'll have a question where you'll have to do this first to find speed and then plug it into this to find something else. Does that make sense? It doesn't matter. Okay, if you're dealing with a period in the context of this, then in all likelihood, you're going to end up with both of these equations, 2 pi r over t, and fc is equal to fg. Let's try these two questions, please.